Hello and welcome to part 3 of our video in chapter 11, Inference About a Mean. We're going to be going over sample size and power. This information is not going to be needed for the test, but it's good to go over it, and because it's not needed for the test, I want to go over it and then help with one of your exercise problems for the homework, which has to deal with power. So I wanted to go through everything. So let's begin. So the sample size and power, 11.7. So these are the questions that we're going to be answering is how big a sample is needed to limit the margin of error to m, how big a sample is needed to test the null hypothesis with 1 minus beta power at the significance level alpha, and what is the power of a test given certain conditions. So to calculate a sample size for confidence intervals, we would take our 1 minus alpha at 100% confidence, or you can raise 100% confidence, whatever confidence interval we're looking for. For mu or mu delta to m, the sample size should be no less than, and this is the equation we would use to find out how big our sample size is needed for a certain confidence interval at a certain confidence level, right? So n equals our z 1 minus alpha over 2 times the standard deviation, or sigma, divided by m, our margin of error, squared. Alpha is our desired level of significance, m is the desired margin of error, and sigma is the population standard deviation. Now once again, our book talks about 30 kind of being this cutoff point for the difference between using a t-table or a z-table. Other people have different points of view on this. You can go online and everybody's going to have their different cutoff points. We'll be always referring back to the book. That is the how the class is laid out. It's the most consistent form that everybody has. So when n is less than 30, or when n is greater than 30, we can substitute a t-score for a z-score. However, when n is less than 30, we want to apply adjustment factor f, which is going to equal to the degrees of freedom plus 3 divided by the degrees of freedom plus 1 to compensate for the difference between z and t. So remember, as t sample size gets larger, it'll be more closely related to a bell-shaped curve in a normal distribution. However, when it's less than 30, our tails are a lot fatter and compensate for a bigger probability. So to kind of adjust for this, we would have this adjustment factor, which we apply to after we figure out our n. So to figure out an n, or a sample size requirement, for our test, our n for our sample size would equal the standard deviation squared times the z 1 minus beta, so our power, plus our z 1 over alpha squared, divided by our delta squared. So our delta, member, is the difference between our two groups. Shown here, delta equals our mu 0 minus mu a is the difference worth detecting. Our standard deviation is the population standard deviation, alpha desired level, and 1 minus beta is desired power of the test. So for one-sided test, you want to use a z of 1 minus alpha in place of a z 1 minus alpha divided by 2 in the formula. That's the difference between one-sided test and two-sided test. Remember, if you're using two sides, you're using both sides of the bell-shaped curve. That's why we divide by 2. And if you're just using a one-sided test, it's just 1 minus alpha. For paired t-tests, remember, you're always going to use sigma delta in place of just regular sigma, or remember, finding the standard deviation of the difference. And then once again, if we might want to apply adjustment factor when n is less than 30 to compensate for the difference between z and t. Power. So when we get to power, power is equal, remember, to 1 minus beta. To calculate power, we have our formula here, where phi is going to equal a negative z1 minus alpha over 2 plus our delta, the absolute value of delta, times by the square root of n over our standard deviation. These just express what they are, and when you find out your phi, that's what you're going to look up in your table B. So it's going to equal to the z-score in table B, and that's going to tell us the power associated with the test. So the book has one example for SIDS birth weight, where it says consider the SIDS illustration in which n equals 10, and it has a standard deviation assumed to be 720 grams. Let alpha of 0.05 two-sided. What is the power of a test under these conditions to detect a mean difference of 300 grams? So we put in our information. Since we know it's alpha 0.05 two-sided, we know that this you should know, commit this to memory, that our z-score is going to be 1.96. So it's going to be a negative 1.96. Our difference between the means is 300 grams. So this is where our delta is. That's 300 grams times by the square root of n, which is 10, divided by 720, which is standard deviation. When you work all this out, you're going to get a negative 0.64. When you look this up in the back, I have a probability of 0.6211, so the power is 26%. This is a very low power. So now on to our exercise problems. Once again, you have an exercise problem, 11.24, not 2 points. Let's change that. 11.24 power. It says a researcher fails to find a significant difference in mean blood pressure in 36 matched pairs. Standard deviation of the difference was 5. What was the power of the test to find a mean difference of 2.5 at alpha equals 0.05 two-sided? So once again, I kind of wrote out, we're calculating power, so we use our power formula, and we have 36 matched pairs, which is going to be our n, and we have our standard deviation of 5 and a mean difference of 2.5, and we want to calculate alpha at 0.05. So we know alpha 0.05 two-sided, like I said, you should commit this to memory, is 1.96. So negative 1.96 plus the absolute value of 2.5 times the square root of 36 over 5. When you put all this in, our answer is going to be 1.04. When you go to the back of the book, table B, and look up 1.04, you will see that we have 85 or 0.8508 or 85%. So our power is 0.8508 or 85% power, and this is relatively good power for the test associated with it. So that's how you calculate power. There's the book example and the one in the back to help you with your homework. Once again, this won't be on a test, but it's good to go over so you understand what it is. And once again, you always want to increase the sample size, because as you increase sample size, the more information you can get out of it, but the more statistically significant it can also be, because we'll be using a z table opposed to a t table as our n increases. So that will do it for this one, and I will see you all in chapter 12. Have a great day.